Hi, we are Stress Tested, presenting our Spring 2026 Capstone project, Signova, a robotic system designed to support ASL education. Our team consists of 4 mechanical engineering students and 1 electrical engineering student from the Georgia Institute of Technology. 90 to 95% of deaf people are born to hearing parents. Most of these parents do not know ASL at the time of birth, creating an immediate communication barrier. In-person ASL tutoring is expensive and limited in supply, while current ASL-specific education tools, like mobile apps and digital programs, teach through video or diagrams, lacking the three-dimensional ability to view signs from multiple angles and the interactivity that is essential for language acquisition.
Learning conversational ASL is highly spatial. It requires both arms and facial expressions. While robotic finger spelling has existed, nothing currently reproduces true conversational-level ASL.
We have designed a torso-up animatronic capable of reproducing conversational ASL. Viewable from all angles, this system is designed for libraries, schools, educational centers, and museums to provide an always available physical ASL teacher.
To remain functional through multiple lessons and events, our system must have a total runtime of at least 4 hours. The animatronic must also be able to sign at least 10 recognizable signs to be an adequate teacher. In order to achieve those 10 signs, one arm of the animatronic should have 21 degrees of freedom, nearly matching that of the human arm. Through computer-aided design, we are able to model all degrees of freedom in our solution for one of 2 arms. Signova has 2 motors at the shoulder, elbow, and wrist for yaw and pitch of the shoulder, extension and flex of the elbow, and roll, yaw, and pitch of the wrist. Each finger is driven by 2 tendons, accounting for the extension and flex, and 1 direct motor connection for spreading the fingers. The thumb has 2 motor connections and 1 tendon, with all motors for tendon connections housed in a hollow forearm.
Before moving into physical prototyping, we conducted analysis on our design to evaluate its performance and identify any necessary improvements. The 2 primary methods we used were linkage analysis and finite element analysis. Linkage analysis was used to determine the minimum spacing required between fingers during motion, while also ensuring the desired range of motion for signing. Using MATLAB, we modeled the kinematics of the tendon-driven finger system to analyze joint angles and motion paths. This allowed us to verify that the fingers could achieve the necessary positions for ASL gestures without exceeding mechanical limits or causing interference between adjacent fingers. Then finite element analysis, or FEA, was used to evaluate how the design would behave under real-world loading conditions. Using SOLIDWORKS' simulation, we simulated applied forces and observed the resulting stress, strain, and displacement within the structure. For this analysis, the system was divided into key components: the fingers, forearm, upper arm, and shoulder. The forces applied to each section were determined beforehand using free body diagrams. Looking at the results, we can highlight a few key findings. For the fingers, the highest stress concentration occurs at the lowest bearing, indicating a potential critical point in the design. However, overall strain in this region remains minimal. In the forearm, elevated stress and strain are observed in the support beam, as highlighted by the green, suggesting areas that may require reinforcement. The upper arm shows noticeable internal strain and displacement, particularly along the vertical cross-section, indicating structural deformation under loading. Finally, the shoulder experiences relatively low stress, strain, and displacement, suggesting it is not a critical failure point in the current design.
Our current prototype is up to the forearm, with the necessary motors for finger actuation mounted in the forearm and the tendons required routed through the fingers into the motors as well. Signova will be manufactured using injection molding, with the 6 molds for fingers and thumbs costing between $1,000 to $1,500, and the 3 molds that make up the palm and wrist being an additional $10,000 to $15,000 per mold. This brings the total cost for a batch of 10,000 units to $65,000, or about $65 in manufacturing costs per product. The chosen material for Signova is nylon, sitting at about $2 per pound, which allows us to produce each arm at under $5. The high tensile strength of 45 to 90 megapascals and lighter density than other plastics allowed it to be the cheapest option that met our needs.
For our next steps, we will develop a prototype that includes the shoulder, torso, and both arms. We will adjust the design of the upper arm so that it is more robust and can support the arm's weight. We will make sure the prototype can accurately create around 30 signs, including all letters and common phrases. And finally, we will conduct fatigue testing to determine how many cycles of usage the design can endure before failure. We would like to acknowledge Dr. Harris and Dr. Ma for their support and guidance throughout this process. Here are our references. Thank you so much for listening, and be sure to check us out at the Design Expo at table W17.